Hey y'all, this is part 2 of Principal Component Analysis. If you haven't watched part 1, I recommend you go back and watch that first, since this video follows from the concepts introduced in part 1. Let's start off with the proportion of variance explained, or PVE. This metric quantifies how much of the total information, or variance, in the data is captured by a single principal component. It is essentially the variance of the mth principal component divided by the variance of all principal components. As we'll see later in the video, this will help us determine how many principal components to keep. But first, to understand this better, we begin with the general definition of population variance for a dataset. Let J represent the jth variable in a linear combination, and Xij represent the ith observation of the jth variable. If we assume the variables have been centered to have a mean of 0, which is common for principal component analysis, we can substitute 0 for the mean. The mean term vanishes, leaving us with the average sum of squares of the jth variable. We then sum up the variance for all variables j from 1 to p to get the total variance as a function of the original predictors. Let's set this definition of total variance aside to use as the denominator in our final equation. Next, we look at the numerator. Recall that the score, ZIM, is a linear combination of the original predictors. Following from the population variance formula from earlier, the variance explained by the mth principal component is the average sum of squares of the scores, ZIM. Substituting the original x values back into the equation yields the following expression. To compute the ratio, we divide the component variance by the total variance to get the proportion of variance explained. The 1/n terms cancel out, leaving us with this ratio as the PVE of the mth principal component. The cumulative PVE can then be obtained by summing the PVEs of the first m components. Summing over all components results in a total of 100%. Finally, connecting back to linear regression, the PVE can be interpreted as the r squared of the approximation of x given by the first m principal components. In linear regression, r squared is defined as the residual sum of squares divided by the total sum of squares. This highlights the direct mathematical relationship between principal component analysis and least squares regression. To visualize the proportion of variance explained, we can use a Scree plot. Consider this plot with 15 principal components. It shows the variance explained by each one. The blue line indicates the proportion of variance explained. In this first example, the first 2 components account for most of the variance, and then the contribution drops off significantly. A Scree plot helps us determine how many components to keep. We look for an elbow point, where the explained variance drops significantly. Here we see a very clear elbow at principal component 3, so we keep the first 2 in our analysis. However, in many real-world cases, the elbow isn't nearly as obvious. Consider this second example. In a plot like this, the decision is pretty ad hoc. Depending on who you ask, the elbow could be seen at different points. One analyst might say it's at component 3, while another might see it at component 7, making this decision quite subjective. Although the decision is often subjective, in supervised settings like principal components regression, we can use techniques like cross-validation to choose objectively. Ultimately, these principal component scores are used in many downstream tasks like regression or clustering, often leading to less noisy and more interpretable results. Principal components regression, or PCR, is a technique that combines principal components and multiple linear regression. It uses principal components as predictors in the regression model. First, we take our predictors and run them through PCA. This step is completely unsupervised, meaning that it doesn't consider the response variable. It just tries to find the best way to summarize the variation in x by finding linear combinations. Once we have the principal components, we feed them into a regression model to predict y. Now we are in supervised territory. We are actively learning the relationship between our components and the target. Because this step is supervised, PCR is a supervised learning method. The underlying assumption of PCR is that the directions in which the predictor variables exhibit the most variation are also the directions most associated with the response variable. If that assumption holds, then fitting least squares to m principal components will lead to better results than fitting least squares to a selection of m original predictors. We can also mitigate overfitting if m is significantly smaller than p. How does the bias-variance trade-off vary as a function of the number of principal components? First, the bias squared. As we add more principal components, our model becomes more flexible and captures more information. Next, there's variance. As we add more components, the model gets more complex and variance starts climbing. When we combine these with the irreducible error, we get the test MSE. It forms this U-shaped curve. Right here is our sweet spot. We've minimized prediction error by balancing bias and variance. If we used all principal components, we'd be on the right, overfitting the data. If we use too few, we underfit. So how do we find the right number of principal components? In practice, we can use cross-validation to find the number of components that minimizes this error. Let's quickly compare the performance of PCR versus shrinkage methods like ridge regression and the lasso. Generally speaking, PCR tends to outperform the others when the true underlying signal is concentrated in just a small number of principal components. A plot of the test MSE can help determine the best model for a particular set of data. And all three methods can offer significant improvements over least squares. PCR is closely related to ridge regression, as both methods address multicollinearity. So ridge regression can be viewed as a continuous version of PCR. Unlike the lasso, PCR does not perform feature selection. Each principal component is a combination of all original predictors, rather than a subset of predictors. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.